atoms that have a positive or a negative charge. That's all they are. It's just something with a charge. They get that charge by gaining or losing electrons. Now, if that doesn't make sense to you to write the E, then go ahead and write the whole word electrons. So we're kind of rolling in from last unit. Everything was about electrons. A lot of this unit is also about the electrons. That's kind of the most important part. Electrons are what do all the bonding, and they're what makes most of the things of properties of when they bond. So if something has a charge, it's because they lost or gained electrons. And why do they do that? We'll get to it. There are two types of anions and cations. There's two types of ions. The anion, I usually remember which one it is, so it has that N in it. And N is the beginning of negative. So ion with a negative charge due to the gaining of electrons. This is kind of like the most backwards thing we'll do all year. Is usually when you think gaining, you think it's going to become positive. Like, oh, I'm gaining something that's positive. No, you're gaining an electron. What charge does an electron have?
Neutral.
You stop.
Guys, negative. Then negative. Try not to look annoyed, but learn it for a long time. Okay? Electrons are negative. Now, if I gain negativity, then you become more negative. So if an atom gains an electron, they become more negative. They are an anion. Now, the ion loses, so I'm going to lose an electron. So I'm literally losing negativity. Then it becomes more positive. So you already got to go ahead and make that switch. If something gains electrons, it is negative because it's gaining a negative thing. If it loses an electron, then it's positive because it's losing a negative thing. Now, however, cation, a little easier. If you think of cats, cats have paws. This is the cutesy way to remember it. So they are positive. They have paws. All right. There's also a T in cation, and T looks like a plus sign. So there's two ways to remember it. If you can remember that cations are positive, then the other one is negative. Yeah. All right, scrolling down. Now, these are the groups on your periodic table that I just made you label. You've already done this. We're just filling it in. In groups 1, it has a +1 charge every time. When something in that first column makes a bond with something else, it will lose an electron. That's what it likes to do. Everyone in that column likes to lose an electron, and they become positive. Everybody in column 2 likes to lose 2 electrons. That's what makes them stable. If they lose 2 electrons, they become positive by 2. In group 3, they like to lose 3 electrons. If they lose 3 negative things, they become positive by 3. Now 4 is where the switch happens. They will either make 4, a +4, or a -4. Either way is just as easy for them. It doesn't matter. Now, something that we have, we're going to talk about more on the next page, but the number they're all trying to get to is either 0 or 8. So if I have valence electrons, we'll talk about more in a second. That's why they go either or, but for now, just believe me, we'll talk about why in a second. So group 5, they're going to be -3. They're always going to want to gain 3 electrons. Group 6 always want to gain 2 electrons. And 7 likes to gain 1, becoming negative by 1. We already wrote that on top of your periodic table. So you should already have it labeled. You should already know. The last group does not form a charge. That last group, remember what it's called? The very last column on the table. What's the family name?
Noble gases.
Noble gases. They are noble because they don't make bonds. That's why they're called noble, because they're stuck up. They don't bond with things. But the reason why they don't bond is because they don't like to lose electrons. They don't like to gain electrons because they're already stable. Everything in that column is a very stable element. They don't need to bond. All right. Going down. Now these, I think I forgot to add this. So let's go ahead and add this to your periodic table. You're going to do it in a second. There are some exceptions to the rule. The exceptions to the rule are these 4 elements Really, aluminum's already in the right spot to have it. But they always make those charges. So on that element, go put that charge. So when I told you that we skipped over the transition metals because they make lots of varying charges, these ones don't. Silver, right here, always makes a +1. Cadmium always makes a +2. Zinc always makes a +2. And aluminum always makes a +3. You just literally write it on the box so you don't forget. Should be adding to your boxes.
Circle.
No, adding to your periodic table.
So do we put in the box that?
In the box, on silver, put a +1. In the box of cadmium, put a +2. In the box of zinc, put a +2. They happen to make this shape on the periodic table. This is AG, this is CD, this is ZN, and this is a +1, this is a +2, +2. Those are 2 in a row and they're +2, that's 1 in a row and it's +1. That's kind of how I remember it. All right, down here. Now if I have bromine, how I do this is I find the periodic table. You already have labeled. Find bromine. Bromine is Br. What charge do we just write above it? We need to find bromine.
-1.
It is -1 because it's on my table too.
Where's AG at?
I said
I think
Br.
it's right there.
Bromine.
Bromine. Now calcium, where's calcium? Ca.
+2.
To +2. So in the second column, I find calcium, so it's a +2. So anytime I ask you what ions they form, you literally just find it on your label periodic table, whatever number it's under, that's what ion it makes. Find nitrogen, which is N.
-3.
-3. N, it's near oxygen.
Game 1, this is game 3. It's game 1, box 2.
Now, when I just told you that negative ions have to gain negativity. So if this is negative by 1, then it's going to gain 1 electron. That's how it became negative by 1. Would have had to gain 1 electron. So if I'm looking at calcium, calcium is +2. To become positive, you have to lose negativity. So how many did calcium lose?
Oh, yeah.
It'd be 2. It's going to lose 2 electrons. So how did it become positive? It had to lose 2 negative things. Yes. So nitrogen is last, guys. I know, but you're talking, and I have a video going where they're trying to listen. So I have a gaining of 3. Last column is how to answer the electron total. Now, normally, when an atom is neutral, the number of electrons it has is just its atomic number. So if I look at bromine, its atomic number is 35. So normally it has 35, but we just said it gained 1 to become negative. So how many does it have now?
35.
No, it gained 1. So it was 35, now it's 36. So then I look at calcium. Calcium is number 20. It loses 2, so now it's 18. I look for nitrogen, which is number 7. It gains 3, so that's 10. Now something I want to point out. When things become an ion, which is what we're talking about, things have these charges. The whole point of why they do this, it's not like some random weirdness. They do it to be stable. So I want you to notice. Guys, we're not done with notes. We didn't say we're done. The next page. Look at these numbers, 36, 18, 10. Look at the noble gas numbers, 36, 18, 10. Those are stable numbers. So the noble gases are already stable. These elements are trying to get to their label. I mean, they're not their label, trying to get to their level of stableness.
So if it's not 36, 18, 10, then
So anytime you're answering these ion electron questions, it's gonna be one of those numbers, 2, 10, 18, 36, 54, 86. Like they're gonna be one of those. All right, scrolling down the next page. Now, just a little more detail of why this happens, and then we're done. We should be on the next page. All right. Now, this is the second thing we labeled for warm-up. It was valence electrons. Valence electrons are the electrons in the outer shell. Meaning, we talked about this last week and the week before that, week before that. If I have one shell around the nucleus, 2, 3, 4. The ones furthest away from the nucleus are my outer shell electrons. Those are valence electrons, the ones on the outermost shell. Now, why they are important? They're more important than literally anything else in an atom. The outermost electrons, they're the most important thing because they are the ones that are going to bond because they're touching the outside world. All these electrons are trapped under other levels. They're not going to bond. They're not going to go out there. These ones are literally touching the outside world and are the ones to bond. So, their driving force among atoms is to gain and lose electrons. They do this to become stable. So we just went over, they're trying to get to that number like noble gases, they're trying to be stable. The stable state is when something has an S2P6. I'm not going to talk about that a lot, that was last unit, but it does relate to this unit, so I'm going to bring it in. If I give you argon's electron configuration, it's 1s2, 2s2, then it's 2p6, 3s2, and then 3p6. That's argon. So if I look at where argon's at the periodic table, that is its electron configuration. That was last unit. Now, what I do to figure out its valence electrons is I look at its outermost shell, meaning the highest number. I got a level 1, I got a level 2, and I have a level 3. So level 3 is my outer shell. How many electrons are in that outer shell? 8. Okay, so what I was saying a second ago, what number are they trying to get to? What is stable? It's 8. 8 for whatever reason. I didn't make the planet. I didn't make the elements. But 8 is the magic number where they are all stable. They don't want to bond anymore. They're happy at 8 when they have 8 on the outside.
8 equals stable?
8 equals stable. I'll probably write that. Sure. 8 equals stable. Nice, helpful phrase. So this element belongs to what column? We already talked about them. The stable column is the noble gases. They already have 8. They naturally have 8 on the outside energy level. They don't need to do anything else. They're already stable. Everything else has to do something to get there. Okay.
What are you doing?
Let's scroll down. Ready? Okay. Now the last bit to understand how these ions get made and how they're trying to become stable is to understand how many valence electrons they have and the fact that they want to have 8. So they don't all have 8, but they want to. Now, before I say that, I want to mention this is like an exception to the rule. I want to underline it. Helium is stable, even though it doesn't have this. It's stable with 2 electrons because how many electrons can one S shell hold? Remember, one sphere, one S. How many electrons can it hold?
8.
That S shell can only hold 2. So helium has a filled S shell. It's filled with 2, so it's stable as well. It doesn't need 8. It's already filled because it only has an S shell. It's a very small atom. So all I'm going to say about that is that helium is small. So is hydrogen. They're very small. So they actually don't need 8. They are fine with 2. So they are full at 2 electrons. But they're the only things that are like that. Everything else on the table wants 8. But hydrogen and helium are cool with 2. And then they stop bonding. So those are our exceptions. All right. Now valence electrons. The total number of electrons present in the final sp configuration is very important. These are the electrons which are involved when atoms bond. That's why they're important. They are the ones that are doing the bonding, are these outside electrons. They are known as valence electrons. I've already said that several times now. The electrons in the outermost energy level, where they're at. They're out there, touching the world, making bonds. The number of valence electrons for representative elements, that means the A group. It's literally labeled on your periodic table. They have A's next to them on the top of the column. It says 1A, 2A, 3A, 4A. So our representative A elements can be determined by just the number they are in. And I already made you underline it. So remember, that was the second thing. I had it highlighted on my table. Some of you did it, some of you have not. But it says 1A. This column has 1 valence electron. This is 2A. This column has 2 valence electrons. We skip the middle. This column says 3A. It has 3 valence electrons. This column says 4A. It has 4 valence electrons. And then when you get down to noble gases, they have 8. Because remember, 8 is our happy magic number. I'm going to scroll down. I'm going to put a little mock periodic table up just to make sure we understood that. So this one has 1 valence electron, this one has 2 valence electrons, this one has 3, 4, 5, 6, out of room, 7, 8. You should have that on your table already. You're just supposed to underline and highlight it. The 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. That's how many valence electrons they have. They have A's in them. All right, now I'm going to find barium. Knowing that barium is in the second column, Ba is in the second column. So how many valence electrons does it have?
2.
Good. 2.
I'm so smart.
Now carbon is in this column. It's in the fourth column. So it has 4. There we go. So all you have to do to know how many valence electrons something has is what column is it in if you have it labeled, which actually it's already labeled for you. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. You just have to remember that label means valence electrons. All right, last thing we're going to do is just talk about a way to draw how many valence electrons something has. This is called a Lewis dot diagram. Lewis dot structure 2. Okay. Now all I do is put the symbol of the element. Sodium is in A. Because we're talking about element symbols, let's remember our quiz is on Friday on element set 3. I posted that list at the top of the week if you forgot. After that, I'm going to put dots around it showing how many valence electrons sodium has. Sodium is in column 1. So it gets 1 dot. But it does matter where you put it. It tells you where to put it. It goes 1, 2, 3, 4, 5, 6, 7, 8. Now, I'll put that chart on there. Like I'll always remind you, I'll put that like number chart on a test so you remember where they go.
So you put it to the right of it up top?
But you put it to the right. So bam.
That is annoying.
It's a dot. I didn't make it up.
What is the point of that order?
Because it shows you where they'd actually go in their P cells. So that's kind of above where y'all understand. Now boron. Boron is B. Boron's in the third column, so that's 3. So again, looking at my dots, I'm gonna have 1 here, I'm gonna have 1 here, and 1 here.
The top left.
1, 2, 3. Boron has 3.
All of them?
How many dots it has? Boron has 3 valence electrons, so I only put 3.
Which one's next?
Oxygen is O.
Negative.
No, that's what it's an ion. So it has a -6 charge, sure, but how many valence electrons does it have? 2. No, it's wrong. What? We're saying numbers confusingly. 6, thank you. Okay. Oxygen is in the 6th column, it's in 6A, so it has 6 valence electrons. So it has 1, 2, 3, 4. This is kind of like how when we were bonding electrons, it'd be 1 on each side first, 1, 2, 3, 4. Then I pair it 5, 6. That's oxygen. And then lastly is argon. Now argon is a noble gas. Noble gases are stable and happy and have all the electrons they need. So the happy number is 8. So when I put argon in there, it's going to be filled. 1, 2, 3, 4, 5, 6, 7, 8. So when you look at a full Lewis dot structure, this is full. This is what they all want to be. They all want to be that. 2 electrons on every side, stable. Now, I'll talk more tomorrow about how that happens, but that's where I'm stopping.
Oh, man. You guys assigned it?
Yes, you do. I'm about to give it to you. All right. That is the end of notes. Y'all do have your worksheet. I'm going to leave up, what do you call it? I'm going to leave up my meet if you need help with it. And I did record it, so I will post this recording. If I went too fast or you missed something, I'll get it posted pretty soon. It just has to load.